Right, this is the Physics 11 lesson on relative velocity. So this is actually the last lesson in our kind of second unit on motion in a plane. So this unit's actually going to involve using our skills that we've already learned about, just calculating velocity, speed, distance, time, as well as what we've just learned with vectors, vector components, and be able to determine velocity from vectors and adding vectors and stuff like that. Okay, so this is kind of the tie it all together lesson, the last one of this unit. Okay, so with relative velocity, again, here's your key term for your vocab list. Relative velocity is the measurement of velocity between two objects in different frames of reference. So the big thing that's different with relative velocity is, for most of the stuff that we've been doing, it's all been from one point of view, right? One frame of reference, and that's how we've been able to assign things as positive or negative, or what we can determine as velocities or speeds. But what often happens is that there's a situation and you're actually dealing with two different frames of references at the same time. Okay, so we'll get into this obviously with the examples, but the first one that we talk about is essentially like someone paddling across a river in a canoe, right? There's the frame of the reference of the person who's in the canoe, who feels as though they are traveling at a particular speed due to how they're paddling. But then there's the frame of reference of the person standing across the stream or the river or whatever it is, and kind of saying, no, they're not going that fast because the current is potentially pushing away from them, right? So the velocity of that particular paddler might be one thing based on the amount of work and force that they're putting into the canoe, but the overall velocity is relative to the overall situation, right? Combined with the multiple frames of reference, right? So that's kind of what we're dealing with here, is how do we combine these two different frames of references into a single, what we call relative velocity, okay? So again, the tricky part with anything, I guess, really physics related is always trying to ask yourself, well, which of these velocities actually have an impact on my answer, right? What am I actually really trying to find? What's relevant? What's not relevant? What needs to be used in a formula and what doesn't? Okay, we're going to go through about 4 examples in class, but again, it's important as you do the practice to kind of keep checking yourself, going, well, is this what I need or is this not what I need? And is this part of the triangle or this part of the triangle? Right? So just kind of the more practice you do, the more familiar you'll start to become with these types of relative velocity problems. Okay. Again, just kind of, we'll be continuing to use trig with all of these types of problems, right? Because we're still going to be creating these right angle triangles, so you'll still need to be, up to speed on your basic trigonometry using sine, cosine, or tangent to either find missing side lengths or missing angles. All right, so we've already been using that a lot, but just as a reminder, it does need to still be used in this section as well. If you need the reminder, there's your wonderful little slide of our classic right angle triangle, SOHCAHTOA trig stuff. So again, this is really just a lesson more on just looking at different problems because each one is slightly different. So we're going to look at 4 together, and then you'll have some questions to try on your own. All right, so here's our first one, and this one is probably one of our easier ones to grasp because it is still only happening in 1 dimension, not in 2, but we'll get into the 2-dimension ones in a minute. So in this one, you have a kayaker who paddles upstream in a river at 4.7 meters per second relative to the water. Right, so again, that's the frame of reference. It's a reference relative to the water of, I'm in the water, this is how fast I can push the water, behind me so that I can move forward. However, observers on the shore note that he is moving at only 2.4 meters per second upstream, right? So every second they're noticing he's only covering a span of 2.4 meters, not the 4.7 that he feels as though he should be covering. That obviously means that there's some sort of current pushing him backwards. And that's what we're trying to determine here. What is the velocity of the current in the river? So let's look at how we would solve that particular problem. All right, so again, with all of these problems, it's good to try and draw somewhat of a diagram in terms of what's actually happening in the scenario, right? So again, using vectors is helpful for that. So what we have to start with is we have our kayaker who's moving in this direction, okay? And we know that our kayaker is moving at a relative speed of 4.7 meters per second, okay? However, it appears to the people on the shore that he's only moving at a speed, so the velocity according to the observers seems to be more like 2.4 meters per second. So the only way that this original vector here turns into this vector here is if we did some sort of addition this way, right? Because we could say that this vector, right, plus this vector would give us this as the resultant, right? So again, if you just kind of thought of it this way, it was kind of like, oh, I did this, and then tip to tail, over top of it, I did this, and then this becomes your resultant vector, right? It's all just one straight line, but that's ultimately our relative velocity, right? A combination of those two velocities that we've been given. So this one ends up being a relatively easy subtraction, right? Because basically the velocity of the kayaker plus the velocity of the current, right, which is this one here, is going to equal the velocity that the observers are noting. We know the velocity of the kayaker, we know the velocity of what the observer sees, we're looking for a velocity of our current. So the velocity of the current is just going to be the velocity of the observer minus the velocity of the kayaker, which means this is going to be 2.4 meters per second minus 4.7 meters per second. Right, and when we do that subtraction, we get a value of negative 2.3 meters per second. And again, it makes sense that that answer is negative because the current is moving in the opposite direction of the kayaker since it's slowing them down, right? If the relative velocity seemed to be bigger, it would mean that the current was actually helping move the kayaker further along, right? So that would mean it would be a positive value, right? So in this case, our current has a speed of 2.3 meters per second in the opposite direction that the kayaker is traveling. Okay, so that's our first one. So like I said, that one starts off pretty straightforward. Again, there's your, your typed out solution if you need it, right? So the current is moving 2.3 meters per second in the opposite direction of the kayaker. So if the kayaker is moving upstream, we can say that the current is downstream. Okay. All right, let's look at one that's a little bit different, right? So bring back the bearings and the dimensions and looking at things kind of with angles. So in this one, we have that a plane's destination is 1.30 times 10 squared kilometers, or 130 kilometers, 30 degrees north of east. So that's where our plane is wanting to go. It travels at 1.20 times 10 squared kilometers per hour, so 120 kilometers per hour in this exact direction, while the wind is blowing at a rate of 40 kilometers per hour due west. Determine the direction the plane is pushed off course and the bearing it must fly in order to reach its destination. So again, with this particular problem, you want to set up, again, the information that you have. Let's go back to the whiteboard. So the first thing we have is that we know that our plane is headed at a bearing of east 30 degrees north, all right? So we know the plane is heading this way, where that angle in there was 30 degrees, okay? We also know that the plane was traveling at a speed of 1.20 times 10 squared kilometers per hour in that direction, right? However, what's happened is even though the plane is headed in this direction, the wind is moving west, right, at 40 kilometers per hour, which means it's getting pushed this way. Okay, so even though the plane is headed in this direction, right, at that exact bearing of where it wants to go, the wind is pushing it here. So a combination of those things gives us that relative velocity, which is like the resultant vector here, right? And we're asked how far is it being thrown off course, right? So in this case, we're not actually being asked to find like what speed, what is its relative velocity. We're being asked to find, well, what is this angle in here, okay? Well, the tricky part with that is that the only way we're actually able to find that angle is if we start by finding this side length, right? So this is kind of all the way back to our adding vectors and how we solve for missing side length. So if we call this just side length x, we will, again, use our law of cosines to be able to find that, because this is actually a 30-degree angle, thanks to our wonderful angle properties, right? Because this is a north-south bearing as well. So here's your z, right? So you can use your alternate interior angle. So there's 30 and that's 30, right? We don't know this angle, nor do we know this one, so we can't just subtract, but we can find x using our law of cosines. So x squared would equal 40 squared plus, I'm just going to turn this into 120 just to make it easier for these quick calculations here, minus 2 times 40 times 120 times the cosine of 30 degrees, right? We do all of that, we get a value of 7,886.156. We then square root, and that gives us a value of 87.67 kilometers per hour, okay? And in that scenario there, right, again, we don't need that relative velocity. What we're looking for is what has it been thrown off course, right? So now that we have this value of our 87.67, we can now just use our law of sines, because now we have a pair to be able to find that missing angle, right? So now we can set up just basically like sine theta over 40 is equal to sine 30 over the 87.67. Multiply both sides by 40, we get sine theta on its own, equaling 0.2281. And then we sine inverse that value, and we get a value of 13 degrees. All right, so the answer to part A here is that our plane is being set 13 degrees off course. Okay, so again, that was what was being asked, right? So it was like we had the wind going due west, we had the plane going north of east, and then it was to determine the direction the plane is being pushed off course and the bearing it must fly in order to reach its destination. So if we know that with a 40 kilometer an hour westward wind, we're going to get blown 13 degrees off course, right, in a northwestern, well, I guess in a western direction, right, then really we should set our course 13 degrees south so that when we actually get thrown off, we're going at the right spot, right? So what I'm saying here is that if this is ultimately, let's kind of try and keep some of this here, right? This is ultimately where we want to end up, right? But that western wind is still going to push us 13 degrees off course, right? So ultimately this is where we want to be. So where we should actually head is a little bit off, so really I just should erase that all, right? So this is where I want to be, right? What's going to end up happening is that if I go 30 degrees, I end up over here. But if I alter my course 13 degrees less, right? So if I take my 30 degrees and I subtract my 13 degrees from it and I get a value of 17 degrees instead, if I only go that value of 17 degrees, right, and then get pushed west, right, I actually end up in the spot that I want to be, right, which is that whole 30 degrees there, right, because that's how much you got pushed off course, okay? So when you're trying to figure out, well, then how much, you know, if you can figure out how much the wind has pushed you off, you can then take that away from the bearing that you're already there, or add it, depending again on the situation, to compensate for how much you're going to get pushed, okay? So basically, if that's what we're doing then what we need to do is set a course for not east 30 degrees north, but instead set a course for east 17 degrees north instead. And that will get us to where we want to go, okay? So there's that one. All right, so again, there's just kind of like the steps that we just went through, right? So we drew the first vector, right? When it's asking you about how much something's getting blown off course, kind of set up your almost addition of vectors, right? Draw your first vector, draw the tail of the second vector, right? So you're going tip to tail, draw your resultant vector. So this is exactly like adding vectors here. You're calculating the angle between the vectors. That's the angle the plane's going to get blown off course, and then compensate this value by adding it to the other side of the plane's motion. So when we added it to the other side of it, what we were saying is, okay, well, instead of, in a way, we were actually kind of subtracting it, but it's adding it to the opposite kind of thing, if you know what I'm getting at there, right? But it's, you're compensating for it, right? So that's what we're dealing with there, right? So again, that would be kind of like a diagram that you would draw. Again, if you had like rulers and protractors and stuff, you could just calculate that just from drawing it and not have to use law of sines and cosines, but we're just calculating people. Okay, right, so again, you get those same results, right? So it was 13, and then we kind of overcompensate that and go just 17 instead. All right, so let's take a look at, again, a different one. It's a very common relative velocity one of this kind of people going across streams, because that's where planes in the air, just because that's where you're getting winds and you're getting currents, and where relative velocity seems to kind of really show up the most in real life. So those are the types of problems you'll see. So in this one, a swimmer is standing on the south shore of a river that is 115 meters wide. He wants to swim straight across and know that he can swim 2.5 meters per second in still water. He drops a stick in the water and finds that it floats with the current 21 meters west in 27 seconds. First part of this question is asking us to determine the direction in which the swimmer should head so that he lands directly across the river on the north bank. All right, we'll come back to part B in a second. All right, so here's where we're at with this one, okay? So what we have is this kind of river that we want to cross, okay? We know that if we drop a stick just straight in the river, right, it's going to travel west. We know that. And in particular, it travels 21 meters in 27 seconds. So again, keep in mind, we're looking at a relative velocity problem, right? We had no information about the time or the distance of the swimmer. We just knew its velocity. So what we need to do is we need to draw a triangle with all velocities, okay? So let's start by finding the velocity of that stick. Okay, so our velocity of the stick, we know travels 21 meters west in 27 seconds. Okay, so the velocity of our stick is 0.78 meters per second in a west direction. Now our swimmer, right, if our swimmer is here and is trying to cross the river, that means that we have a current that's clearly moving west. If we drop the stick in the water and it's pushed west on its own, then we clearly have a current here. So our swimmer might start by heading out this way, right? That's obviously where it wants to go. But what ends up happening is that it gets pulled, swimmer is going to get pulled to the west in that sense, right? So this velocity, this is our stick, is our 0.78 meters per second. This line here is representing our swimmer, right? Because even though that's the direction it was heading, this is actually where it ended up going. So the velocity of our swimmer relative to the water is that 2.5 meters per second. And we've been asked, what's the angle that it gets pushed across, right? They wanted to go straight north, but it obviously gets pushed, right? What's that angle there? What's nice about this particular problem is that it's not a weird triangle. It's a right angle triangle, right? Because it was wanting to go straight north, and that went exactly west. So we get this nice right angle triangle, and hey, we can solve for that missing angle relatively easily, right? Using, in this case, we'd use a sine ratio, right? Because here's the angle we want to find, that's the opposite, and that's the hypotenuse. So we can set up sine theta is equal to the opposite, which was the 0.78, divided by the hypotenuse, which is the 2.5, and then we would just do sine inverse of that, right? So sine inverse, put that in, of the 0.78 divided by the 2.5, and we end up getting a value of 18.18 degrees, but we only get 2 sig figs because of that 21 plus the 2.5 actually, so 18 degrees. right? So our swimmer is being pushed, so our answer to A is that the swimmer is pushed 18 degrees off course, right? So if it's going to get pushed 18 degrees off course and it wants to end up here, what we should instead do is head 18 degrees in this direction, right? So that when the current pulls us this way, we actually end up exactly where we want to go, right? So swimmer should head in a direction of, so again, we want this to be the 18 degrees, so that would be north 18 degrees east. Okay, so that's where the direction the swimmer should actually go in. All right, let's go back to part B of this question because we weren't done. All right, part B of this question says, if he follows your advice, right, so if he actually does do that 18 degrees, north 18 degrees east, how long is it going to take him to cross that river? And this is where we use that piece of information that the river is 115 meters wide. Okay, so we're going to look at that triangle again in just a slightly different way, and we're trying to figure out how long it's going to reach him to reach, how long it will take to reach the far shore. All right, so we kind of have to redraw that triangle and say, all right, well now my swimmer isn't going to head straight north. Our swimmer is going to head off in this direction here, right, at that speed of the 2.5 meters per second at an angle of 18 degrees, north 18 degrees east. And we know the current is going to push in this direction with a speed of 0.78 meters per second, right? And again, because of that, we end up exactly over here, right? So we're trying to figure out, well, what is this velocity, right? Well, again, we know that velocity is equal to distance, or displacement, sorry, divided by time. Okay, well, it's all well and good, but we just don't know that velocity because the question was asking how long is it going to take us to get there. We do know that that distance there, or that displacement, is 115 meters, but I can't solve for t unless I actually have v here, right? Because I can rearrange this formula and say that time is going to equal to distance divided by velocity, right? Now, since this is representing the river, okay, we need, well, what would be the velocity in terms of the relative velocity just going straight, right? Because that 115 meters is just straight across. So in order for me to accurately, it's kind of going back to vector components here, in order to accurately determine, well, what's the speed, right, or the relative velocity going straight across, I need to kind of use these two pieces of information as well, right? So this velocity can be found, since these two are velocities, this would also give me the relative velocity of just going straight up. I can solve that by just using, either pick the trig, you can either just use Pythagorean theorem, because you have 2 out of 3 sides of a right angle triangle, right? Or if you want, you can use the 18 degrees and use sine, actually you'd use tan, or you'd use cosine to get that value, right? And the choice is yours. I mean, I just kind of used Pythagorean theorem, right, because we knew that that 18 degrees was a rounded answer anyway, but that value of v is just going to be found by using Pythagorean theorem, so it was 2.5 squared minus the 0.78 squared, and then square rooted, and when you do that, you get this velocity of 2.375 meters per second. Okay, so if, like, let's say this is the swimmer, right, and let's say this is their friend waiting exactly north, right, the swimmer feels as though they are swimming at a speed of 2.5 meters per second. That's relative to them in the water. However, the observer is only noticing how they're coming straight at them, which is at a speed of 2.375 meters per second, because obviously their northward motion has been reduced due to the current pulling west. Okay, so again, it's all kind of, you got to work in one dimension. So since this was a two-dimensional thing, but the river was just a one dimension going straight across, we have to kind of figure, well, what is just the one dimension velocity, so I can figure out that one dimension time. Okay, so once I find that, my time is now going to equal that 115 meters divided by that just northward velocity of 2.375 meters per second. And then that quick little division gives me an answer of 48.4 seconds, but I only get 2 sig figs, so I'm going to call it just 48. Okay, so I can cross the river in 48 seconds, right? Notice how, again, I wasn't just using that 2.5 meters per second. Oh, that's how fast he's swimming, and it's 115 meters. Well, no, because it's the 2.5 meters per second, but he's being pulled. Right? If there was no current, then sure, go find your time by taking that 115 divided by 2.5. But because of that current that's pulling it back, the overall speed has kind of been reduced, so we need to figure out what that is before we can do that division. Okay? Tricky stuff, but I think we can do it. All right. This one, if we were in class, I would have said, okay, now it's time for independent practice. Right, but since we're not, I'm just going to give you another example. I just blew through those last 2 slides, but again, this was just kind of like, again, for this type of problem, what we kind of did there was we found the velocity of the stick first, we drew that properly labeled diagram, we calculated the angle, we used the vectors to show the velocity of the current, the velocity which a swimmer must travel, used Pythagorean theorem, and then found time. Okay, that was essentially what we did, and then here's the worked out solutions that I just basically did for you on the board. Okay. Now, where were we here? Yeah, so here in independent practice, right? So here, what we end up looking at is a plane, okay? In this one, we're back to a plane. So the plane wants to travel east. The plane has a velocity of 500 kilometers per hour relative to the air, right? So if we're thinking there's no wind pushing it anyway, it can travel at a velocity of 500 kilometers per hour. But if in this situation there is a wind that's blowing at 50 kilometers per hour north, calculate the proper heading that the plane should actually use. Okay, so again, this is a similar one where it's like, well, the plane wants to go in one direction, but it's going to get blown in a different direction. How do we kind of, one, set that up, right? What does that triangle look like? And then what does that angle look like? So let's go back and do that problem on the whiteboard. Okay, so again, what's happening is that the plane would like to travel east, right? Ultimately, like if this is our starting point, this is where the plane would like to end up, and it might start trying to head in that direction, but we know that there's a wind that's pushing north, right? So that north wind absolutely is part of our problem, right? And that north wind is happening at 50 kilometers per hour. Our plane started from over here. It wanted to go in this bearing, right? But really what it ended up doing was this. Right? It was heading east, but it got pushed north, right? So it's kind of like, all right, it was wanting to do this, right? But the wind pushed it this way, going at this speed. Where are we going to put that 500 kilometers an hour, right? Well, which one actually represents the plane? Well, this is what the plane wanted to do, but it's not actually what the plane did. This is the line that actually represents the plane and the plane speed, so this is what gets the 500 kilometer an hour velocity. Okay, so the first part again of this question is asking how far is the plane, going to be blown off course, and how should it actually change its course, right? Well, let's figure out this angle, right? Because this is what it wanted to do. This is what it ended up doing. How far off is that? So again, this would be a sine ratio because that's the opposite and that's the hypotenuse. So we can go sine theta is equal to opposite over hypotenuse. So that's just going to be the sine inverse of that ratio. and that's just 5.7, excuse me, 5.74, or just 5.7. So let's just leave it at 7.4 right now, degrees. So it gets blown 5.74 degrees off course, which means if it wants to end up over here, and it's going to end up going north, what I should do is aim 5.74 degrees down this way, so that when the wind pushes me up, I end up exactly east from where I started, right? So because of that, the plane should head east 5.74 degrees south. Right? That should be the bearing that the plane wants to go in order to get exactly east. Okay? Let's see what part B was asking us for this one. So part B says that the magnitude of the plane's velocity relative to the ground, so that's what we're trying to calculate. Calculate the magnitude of the plane's velocity relative to the ground in kilometers per hour should the plane use the heading determined in part A. Okay, so again, this is where we get that relative velocity, right? So in the air, the plane feels, and it's probably, equipment is telling it that it's traveling at 500 kilometers per hour. But if we were an observer on the ground, we're going to say, well, no, it doesn't actually seem as though you're traveling that fast, because in this direction towards me, you've actually been slowed down because of this wind pushing you in a different direction. Okay, so you can already see that obviously it's a little bit smaller in the answer, but let's show how we get that. Okay, so again, in this case, if we follow the direction, and our plane is actually going to head slightly, right, 5.74 degrees south of east, right? That's the plane, right? This is now the plane's motion, so that gets the 500 kilometers per hour mark. The wind is still pushing at 50 kilometers per hour north, and we are trying to figure out, right, relative to, again, this person standing over here on the ground being like, oh, how fast is that plane coming at me straight from the west coming to the east? What is this velocity here, right? And once again, this is a nice little right angle triangle, and we can find that relative velocity just through Pythagorean theorem, right? So that's going to equal the square root of 500 squared minus 50 squared, and we do that, and that's what gives you this value of 497.5 kilometers per hour. I think we only get 3 sig figs in this problem, so I think that ended up rounding like a 4.8 or something like that. So we actually would just use 497. And that's the plane's relative velocity. Okay, so again, it's like from the ground, right? Relative velocity from the ground. The person who's on the ground looking at, okay, how fast is the plane coming, over, like passing over my head. It's not as quick as what the plane's instruments are telling it's traveling, because the wind is pushing it in a different direction, right? Which alters its relative velocity to the observer. Okay. All right, so that's that lesson on relative velocity. Again, there's the solutions. What I'm going to be posting along with this is just a set of textbook questions. It's actually not questions from the textbook you have per se. I have and what I mean by that is just in terms of the page number and the actual numbers there. I have a digital copy of it's a different version of the same textbook that you have, but because of it, the page numbers and the numbers are different because they ordered things a little bit differently. And I know a lot of you actually maybe didn't bring your textbooks home from the school and you can't get them. So what I'm actually going to be doing is taking just a PDF of these questions, and I'll post those. All right, so you don't actually have to go get your textbook. You can just look directly at the questions that I've posted, because like I said, your page 110 and those questions might not add up. Match up to these particular ones. So just look at the document that I post that has these questions, and of course the solutions will be there too. Again, I think the trickiest thing in this particular unit is going to be figuring out, well, when I draw my diagram, which ones go where, right? Try and really think about what's representing the object that's moving with that particular speed, and if it's traveling at an angle, then that's the speed that's the part of the triangle that needs to get that speed, okay? But again, doing these practice problems is going to help you figure that out, okay? So I'll leave that with you. Like I said, this is the last little section of our unit. So what I'm going to be doing after this, just kind of try and talk to you a little bit with my face here. After this, you're just going to get like a relative velocity check-in. I'm suspecting that these questions might be a little bit tricky, so I'll probably be scheduling another Google Meet session at some point like later this week, maybe on Friday, if not on Monday, the latest. And then I'm just going to be giving you like a check-in, just similar to what we did with the freely falling objects. It's like a 2-question check-in, maybe just a one, not sure yet, 1 or 2 question check-in on the relative velocity, and then we basically are just going to be moving on. I'll also post an opportunity for you to upload your vocabs at that point, because like I said, this is our last lesson for this unit, and then we'll be moving on, right? It's not really a way for me to do real testing at this point, so just kind of check-ins and assignments are what we can do for right now. All right, so that's the plan, and I'll be in touch.